Hey guys, welcome to your final lesson in Unit 8, where we're going to be talking about electrolysis and electrolytic cells, which are actually going to be the opposite of our galvanic or voltaic cells that we've been focused on up to this point. So when we're talking about electrolysis and electrolytic cells, I want to first define some things for you. So electrolysis is the passing of a direct electrical current through an electrolyte. So remember, an electrolyte is just something that will pass an electrical current along. And it produces chemical reactions at the electrodes and typically involves the decomposition of materials. So if we put electrolysis and we put it into an actual electrochemical cell, we call it an electrolytic cell. And so what an electrolytic cell is it's forcing current through that cell to create a chemical reaction when its normal cell potential would be negative. So what we mean by that is in a galvanic cell, of course, we have a spontaneous redox reaction where these electrons are going to move spontaneously because this reduction potential is higher, and so it pulls the electrons and it's going to create energy through the chemical reaction. An electrolytic cell is going to run this same reaction, for example, but in the reverse direction. And so if it is spontaneous in the forward direction with a negative delta G, then it is non-spontaneous in the reverse direction as a positive delta G. And so the only way that that's going to happen is with an external input of energy. So I want you to notice something. The electrons are still flowing anode to cathode, even in the electrolytic cell. So just like we learned with the galvanic cell, electrons always move away from the anode and they come to the cathode. But instead of doing that spontaneously, we are forcing them to run that direction by putting that external input of energy. So here's an actual example where we have real substances instead of X's and Y's. In a galvanic cell, it's our chemical reaction, the redox reaction that produces our current, right? And so in this galvanic cell on the left-hand side, we have a voltage of 0.74. Which makes sense because if we look down here at our cell potentials, we have negative 0.4 for cadmium and 0.34 for copper. And since this is a galvanic cell, the metal with the substance with the higher reduction potential is being reduced at the cathode. And so we do cathode minus anode, so 0.34 minus negative 0.4. And that gives me positive 0.74 volts. So that's our voltage that's produced in our galvanic cell. Now I want you to look at the right-hand side at our electrolytic cell. Now look what's being reduced. Cadmium is being reduced, which has a lower reduction potential. So when we calculate cathode minus anode here, we have negative 0.4 minus 0.34. So we get negative 0.74. So this reaction is not going to occur spontaneously. We have the thing with the lower reduction potential being reduced. But we're forcing it to occur by having an external input of energy. We're forcing the electrons to flow from copper to cadmium. So again, I want you to note the electrons are still going anode to cathode, and it's still reduction happening at the cathode, oxidation happening at the anode. We're just forcing the electrons to go from the thing with the lower reduction potential to the higher. So we're having the lower reduction potential be the one being reduced. So we're forcing it to run in the non-spontaneous direction. Why would we do that? Well, we have multiple examples of applications of electrolysis. The first is metal plating. We can use electrolysis to put an object in and actually plate certain metals, like cover the external part of it with a different metal. So for example, tin cans are actually made of steel. They're just plated with tin on the outside. Chrome plated steel for like bumpers or hubcaps or different things. We have galvanized steel. We have silver-plated cutlery. Lots of different examples of plating a metal onto another object. And again, what that term plating means is that we're taking aqueous ions of it and then we're turning it into solid and coating the outside of it. So we're reducing the metal onto the other object. So this is like this right here, this spoon is serving as an electrode, and with this battery, so with this external input of energy, we're forcing electrons to flow this way. It's going to attach to the positive silver, which is going to plate it onto the outside of that spoon. So as we just mentioned, electroplating is using electrolysis to deposit a neutral metal onto an electrode by reducing those metals that are in solution. So we're running a reduction reaction is causing aqueous ions to plate onto the electrode. So we can actually calculate exactly how much we can plate or how long it would take to plate a certain amount as long as we have our time and our current. All right, so here's an example. We have copper. So if we want to kind of visualize what's going to be happening here, we've got a solution. It's going to have copper 2+ ions. We have some electrode in here. And what's going to happen as electrons flow and they reach the copper 2+ ions, they get reduced, right, into copper. And so that solid copper is going to plate onto the outside of this electrode. Now we are told that we're passing a current of 10 amps. Okay, now you are told on your reference sheet that we have a variable for current. It is I, and its unit is amps. And then you are told that we have Q is charge in coulombs. And then we have T equals time in seconds. And then you're given this equation, I equals Q over T. So current is equal to charge over time, or in other words, amps are equal to coulombs per second. I just plugged the units in. So I say all of that to say 10 amps just means 10 coulombs per second passing through. So every second there's 10 coulombs of charge passing through. Now, if you see 10 amps and you're like, I don't have a conversion factor with amps, but I have one for coulombs, just remember whatever amps you're given, it's that many coulombs per second. If you want to have to look it up and remember this equation, it's charge over time, so it's coulombs over seconds, go for it. But just remember, if you're given amps, it's that many coulombs per second, okay? Once we know the coulombs, we know the current, we can actually convert everything into mass over time. We can see exactly how much, because it tells us here that we're doing it for 30 minutes. All right. All right, y'all. So if you remember from the previous slide, we were given the current of 10 amps, which I explained to you just means 10 coulombs per second. And we were told that we were running it for 30 minutes, okay? We're just going to set this up like a conversion factor. So we are going to start with 30 minutes because I usually like to start my conversion with the thing that I only have one of. So like 30 minutes doesn't have anything down here at the bottom. If you start with 10 coulombs per second, you're still going to end up with the same answer. I just like to start with the time. All right, so we have 30 minutes. Well, I know how many coulombs per second, so I need to convert this to seconds. So 1 minute is 60 seconds. Now, the next conversion factor that I have that deals with seconds, because that's what I'm in now, is 10 coulombs per second. So every 1 second, 10 coulombs passes through. Now, I got to figure out what conversion do I have with coulombs. Well, if you look on your equation sheet, you are given Faraday's constant, which we actually used earlier when we were calculating Gibbs free energy. Faraday's constant is 96,485 coulombs per mole of electrons. Remember, Faraday's constant told us exactly how much charge there is per mole of electron. Well, I have 10 coulombs, and then we're going to put 96,485 coulombs per mole of electron. Now, remember, we're dealing with copper. We're reducing copper. That's what we were told in our problem. So how many moles of electrons are needed for each copper? It's 2 electrons. So 2 moles of electrons for every 1 mole of copper. Now, I wanted to know the mass that would be plated. So then 1 mole of copper is 63.55 grams. Remember, just get that straight from the periodic table. Then I multiply across the top, I multiply across the bottom, and divide those two numbers, and I'm going to get 5.94 grams of copper. So I calculated exactly how much copper would be plated if I ran a current of 10 amps for 30 minutes. So let's do a couple practice problems. Now notice this time we are not given the time. We are asked to determine the time. So how long must a current of 5 amps, so just immediately say that's 5 coulombs per second, solution of silver plus to produce 10.5 grams of silver. So this time we're actually starting with our mass. So we're kind of working backwards from what we did in the previous slide. Well, I know I'm going to need to get to moles of electrons. So first I need to get to moles of silver. So 1 mole of silver is 107.9 grams, just straight from the periodic table. And then 1 mole of silver is going to need 1 electron. So we have that 1 electron, so 1 mole of electrons. And then Faraday's constant tells me that for 1 mole of electrons, we have 96,485 coulombs of charge. And then it told me that I was running this at 5 coulombs per second. Now, it just says how long, so it doesn't tell me I need to report in any certain unit of time. So if I leave it here, that gives me 1,878 seconds. Now, we don't often use seconds to do long periods of time. So if we wanted to, we could also say that there's 60 seconds in a minute. And when you do that, you get 31.3 minutes. But it did not specify, so if you answered 1,878 seconds, that would not be incorrect. So this time we went from mass to time. All right, here we are looking for mass again. So this is like the first problem. What mass of cobalt from cobalt 2 plus can be produced in 1 hour with a current of 15 amps? So 15 amps, we'll immediately say, is just 15 coulombs per second. So I'm going to start with 1 hour. I know I need to get into seconds because my conversion is coulombs per second. So 1 hour is 60 minutes. 1 minute is 60 seconds. Now I can use my 15 coulombs per every second. And then I know that a mole of electrons is equal to 96,485 coulombs. And it told me here that it is, oh, whoops, sorry, hold on. We're at moles of electron. I need 2 moles of electron for every 1 mole of cobalt. Because remember, cobalt 2 plus would need 2 electrons. And then we know that a mole of cobalt, sorry, I tried to skip a step there, is equal to 58.9 grams. So we got to remember, this is moles of electrons. This is just moles of cobalt. So we got to be careful there. Skip that last step. So multiply across the top, multiply across the bottom, and divide, and I get 16.5 grams of cobalt. So that's really the main math or calculations that you're going to have to do with electrolysis and electrolytic cells. The last thing I wanted to go through are just some everyday examples or applications of electrochemistry, so of both galvanic and electrolytic. So batteries are a great example of galvanic cells. So batteries at their very basic structure are galvanic cells or groups of galvanic cells where their total potential adds up to the battery's potential. So an example is something called a lead storage battery. That's the battery that would be in your car. So they're specifically made to function for several years at a wide variety of temperatures. The anode is lead and the cathode is lead that's been coated with lead dioxide. And so you can see those two reactions that are happening at both the anode and then the cathode. And it's that chemical redox reaction that supplies the energy that then your car uses to run. Corrosion is a real life example of a redox reaction that we have had to figure out ways to try to prevent. So corrosion is the degradation of metals due to that redox reaction. It's the actually oxidation of metals. So we know oxygen gas is a huge component of our atmosphere. Well, if you look at the reduction potentials that I have on the screen, the one I have at the very top is oxygen. And so if you notice below that, I'm going to point out a few. We've got copper, lead, iron, tin, nickel, zinc, aluminum. Those are all those metals that you are familiar with because we make lots of materials out of them. And the issue is all of those that I just named have a lower reduction potential than oxygen. So oxygen is going to be reduced by all of those metals, meaning they are oxidized. And what happens when they are oxidized is they degrade, or sometimes we call it rusting. So because we have this issue of corrosion, we have come up with a few different ways that we can prevent it or slow it down. A lot of things we do is usually paint or plate a coating. Some examples are chromium, aluminum, and tin. Those are often used to plate over steel because they actually, when they are combined with oxygen, they create an oxide. So for example, they make aluminum oxide, which then protects the inner metal. So a lot of cars now have a coating of aluminum, but it's actually, aluminum is not a magnetic metal. So it was something interesting I realized because my dad tried, when he got a new truck, he tried to move his car magnets from his old car to his truck, and they wouldn't stick, and that's because his truck is an aluminum body truck. But that's because it forms an oxide coating instead of corroding and rusting. Zinc is often used with a process called galvanizing. So when something is coated in zinc, it's called galvanizing. So you may have heard like galvanized steel before. Zinc has the lowest reduction potential compared to a lot of our other metals, and so it kind of serves as a sacrifice. So it'll get corroded, but the inner layer of whatever that metal is will not. Stainless steel is another example. It's an alloy, so a metal mixture of chromium and nickel, both of which form that oxide coating, which changes the reduction potential and keeps it from being corroded. And then sometimes when we have certain things we need to protect, we'll add what's called a sacrificial anode. So we connect whatever thing we don't want to corrode to a metal that has is more active, and so then it's actually going to that metal is going to be corroded instead of the thing that we're trying to protect. So just an interesting example of a real use of our knowledge of redox reactions and reduction potentials. Some examples of electrolysis. Of sodium metal is produced through the electrolysis of molten sodium chloride, which is kind of weird to think about because sodium chloride obviously is an ionic compound, so it doesn't really liquefy. It gets to a molten state, but then they can actually set up electrolysis where they put in that external energy and they force a non-spontaneous reaction to happen, which forms sodium metal, which they can cool down and solid sodium. Electrolysis of water is another example. It forces the non-spontaneous decomposition of water. We all know and should know that water doesn't decompose on its own, right? We don't have a glass of water sitting on the table and all of a sudden it's oxygen and hydrogen gas. That would be bad. But we can force that to happen with an external input of energy through electrolysis, and this produces hydrogen gas and oxygen gas, and this is how like a hydrogen fuel cell would work. We got to produce that hydrogen gas and then use it for energy. So just some examples. I'm not going to put a test question with these real world applications, but sometimes when we can throw them in there, it's nice for you to actually see where this chemistry plays out in real life. So that's it for Unit 8, and I will see you again in Unit 9.